So in this question, we're going to be looking at an emission spectrum and how they are created by the emission of photons. Now we're given the energy level diagram for the hydrogen atom. So we have our ground state at minus 22 times 10 to the minus 19 joules, all the way up to our ionization state, where effectively the energy is 0. Now the first part of the question is a wordy, explainy question, and it's worth 3 marks. It wants you to explain how changes of electron energies can produce a line emission spectrum. So you're looking to have at least 3 points in this and have it be well written in order to get your 3 marks, but it's always good to include extra info if you can. So whenever we're talking about this, and about absorption spectra or emission spectra, the first thing to note, and of course you won't bullet point this, you will write it out in full, is that electrons in an atom can only exist at discrete energy levels. Okay, so that's our first point that we need to write in. We then need to say that when an electron falls from a higher energy level to a lower one, it emits a photon. Then we need to say that the photon energy is equal to the difference in energy levels and since E equals hc over lambda, each transition produces a photon of a definite wavelength. So that's how our spectra is created. Now the next question is a nice simple one. It says, what is meant by ionization? And ionization is just when an electron, and again write this out in full, is removed from an atom. So in terms of what's happening with our energy levels, it's able to get all the way up to the ionization level. The next part of the question says, state the energy in joules required to ionize a hydrogen atom from its ground state. Well, if we have a look back at our diagram, the ground state is at minus 22 times 10 to the minus 19 joules, and it's got to get all the way up to 0. So it has to gain 22 times 10 to the minus 19 joules, or the difference in energy between our ionization level here at 0 joules and our ground state at minus 22. So the energy needed to ionize it is simply 22 times 10 to the minus 19 joules, and we could tidy that up, stick it in standard form, 2.2 times 10 to the minus 18 joules. It's then saying calculate the minimum frequency of radiation that can ionize a hydrogen from its ground state. Well, we know that the energy needed to ionize an electron from its ground state is 2.2 times 10 to the 18 joules. And we know that that is equal, and this time it's asking for the frequency, so it's equal to HF. So if we rearrange this to get the F, and that's our minimum frequency, is equal to the energy difference in our levels divided by H, and we plug our 2.2 times 10 to the 18 minus 18 in for our E, and our 6.63 times 10 to the minus 34 for our H, Planck's constant, we end up getting a value of 3.3 times 10 to the 15 Hertz. Then we're asked what happens to an electron in the ground state of a hydrogen atom when it receives radiation of a frequency greater than that minimum frequency that we've just worked out. Well, if it has exactly the minimum frequency, the electron will just be released. But if it has more energy than the energy required to raise it from the ground state to the ionization level, then that excess energy gets converted into kinetic energy. So our electron will gain kinetic energy. And the final part of the question wants us to calculate the wavelength of radiation when an electron falls from n equals 3 to n equals 2. So if we go back up to our energy level diagram, we have it falling from n equals 3 to n equals 2, and to do that it emits a photon of light, where the photon energy is equal to our higher energy level minus our lower energy level, which in this case is equal to the n equals 3, which is minus 2.4 times 10 to the minus 19 joules, minus 5.4 times 10 to the minus 19 joules. And when I plug those numbers into the equation, I get a photon energy equal to 3 times 10 to the minus 19 joules. That gives me my energy. I've been asked to find the wavelength, and I know that the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength. I want to find the wavelength, so I rearrange that equation to get wavelength equals hc over E, where E is my difference in energy levels, which I have calculated up there. H is Planck's constant, 6.63 times 10 to the minus 34. C is the speed of light, 3 times 10 to the 8. When I plug those numbers into my equation, I end up getting a wavelength, which is equal to 6.6 times 10 to the minus 7 meters. And the question doesn't ask it, but it's worth thinking, that is just within the visible range of 4 to 7 times 10 to the minus 7 meters.